You don't need to restart this. So band model. And the band model is talking about the same thing, okay? But from the energy perspective. So here, for example, for the hydrogen molecule, we are talking about the energy level. You have those two levels. In the bonding and anti-bonding, you have the split. But this only applies to two atoms. For the silicon solids, you have so many atoms. So you have to consider the band because there are many levels. So they form a band. And we have the split of the band into these filled states and empty states. Similarly as that bonding and anti-bonding level in the single molecule. So here, for the filled states, it's filled with electrons. Empty states are empty. This is at the absolute zero temperature, T equals to 0 Kelvin. And then in the middle, those are called band gap. That means there's no available states for the electron. So electrons are not allowed in the band gap. And this is when you have some finite temperature, you may have some probability to excite the electron from the filled states to the empty states. So you leave behind a vacancy in the filled states that is a hole. So you create the electron and hole pair in this way from the energy perspective. But essentially, if you look at the bound model and band model, they're talking about the same physics here.
Why can't any electrons be in the band gap? Because aren't they like partially filled states?
No, there's no available states in the band gap. It's like the bonding and anti-bonding level. Between that, there's no available states for the electrons to stay.
Oh, okay.
Yeah, so that is not allowed. So here, we are talking about the same physics, but using different model or different perspective. So here, for example, the bond breaking, the generation of the electron and hole pair from the bond model, and here from the energy band diagram point of view, we are talking about the electron jumping from the filled states to the empty states. So this is the same physics, different perspective. And then let's look at the differences between metals, semiconductors, and insulators from the band diagram point of view. So we talk about that in our integrated circuits. On the chip, we use the metals for the interconnect. And then the semiconductor, for example, silicon as a substrate to build your transistor. And then the insulators to isolate the metals and the semiconductors. So the essential difference here is from the energy band point of view is the difference in the band gap. So if you look at the semiconductor and the insulator, both of them will have two separated states. One is filled states, one is empty states. And for example here, for the semiconductor, we have silicon here. And the silicon has the band gap. We use Eg, represent the band gap. And Eg has a number 1.1 electron volts. So here the EV is electron volts, which is a unit of energy. So it's a unit of energy. Essentially, you can convert that to joule. So electron volts means you use 1 volt, the voltage, to move that 1 electron. That is the energy you use. So this is a unit of energy. And silicon has a value 1.1. And if you look at the silicon dioxide, which is the insulator, it's an oxide. So the EG is 9 eV. It's much larger. So my question is, with this much larger band gap, why this silicon dioxide becomes insulator?
Chance of an electron going from the valence state to the empty state is
Yeah.
very less electron.
Yes. So we talked about earlier, right? So we rely on that thermal energy to excite the electrons from the filled state to the empty states. So if this band gap is larger, so it's more difficult to make the electrons jump from the filled states to the empty states. So you have much less free electrons in the empty states. So it's very hard to conduct this insulator. For the metal, the empty states and the filled states overlap. So in other words, the EG is 0. There's no band gap in the metal. Then that means in the empty states, you will have many electrons. All empty states are partially filled. Then if it's a partially filled, then you have the electrons moving around. That means you can conduct. So it's a metal. But here you look at the insulator and the semiconductor. Actually, there's no clear boundary between the insulator and the semiconductor. So in practice, we think that EG larger than 4 eV is more like an insulator, and EG less than 4 eV is more like semiconductor. But there's no clear boundary. There are many other semiconductor materials other than silicon. For example, we just mentioned germanium. And germanium has a little bit smaller band gap, about 0.6 eV. So any questions here? Yes?
Is gallium also used as a semiconductor?
Gallium?
Gallium.
Ga?
Yeah.
Ga is where is Ga in the periodic table? It's because gallium, I think the elemental form of gallium is not very stable. So the elemental form of gallium is not very stable. I mean Ga here. This is more like a metal because it's even after aluminum. Of course, gallium is not that conductive, but I think it's not very stable. So another very common semiconductor is gallium arsenide, GaAs. So which is a very high mobility semiconductor used for your wireless communication circuits, like your LTE kind of high speed, high frequency circuits are typically made of this gallium arsenide semiconductor for the communication. But for digital computing, people use silicon. All right. So that's the end of this lecture 4.